Sorry, I know I'm moving my camera around a little bit here. So if I make this substitution into this term right here and I replace it with the change in U, here's what we get. Okay, this is sort of a step that I wanted to show even though it's pretty simple. Well, we know that the total work done on an object is equal to the change in kinetic energy. Okay, so now I'm going to substitute in for this. When I do that, I get to this equation right here. So now I've got the total change in kinetic energy of a system plus the total change in potential energy of a system is equal to all work done by forces outside the system, work external, plus any work done by non-conservative forces like friction or forces applied or other forces that are non-conservative. So this is just restating this whole idea. Now, if I define this following quantity right here, I'm gonna introduce a quantity called mechanical energy. But if you take the change in the kinetic energy plus the change in the potential energy, that's the same saying as the change in each one added together, okay? This quantity, if I take at any given moment the kinetic energy plus the potential energy, this is called the total mechanical energy. This is a definition. Mechanical energy is the combination of kinetic and potential, okay? So this got rewritten as this, and then we defined this thing inside the parentheses as mechanical energy. So this is really just the total change in mechanical energy. This becomes a very, very important result because once I rearrange it, I get this idea right here. And here's what I did. From here, I subtracted work done by non-conservative over to this side, and this whole thing got replaced with change in mechanical. So it goes from here to here. And what we have left is work done by forces outside the system is equal to the total change in mechanical energy inside the system minus any work lost. So this is like a loss term right here. This is like the idea that when you're running a car, you lose some of your input energy to friction created by the parts, and that heat leaves the system, okay? So this is all the changes inside the system. This would be anything that leaves the system. This is work done by non-conservative forces. The difference between these two is equal to the total work done by forces outside the system. This result is called the work energy theorem for systems. This is a very large idea. This is like governing the entire universe idea. What's nice about this for what we do, and this is where I'm going to start to do some examples in class next time, often we can talk about a system in such a way that we are able to ignore the non-conservative system, the non-conservative forces, which means that this term goes away. We are also usually able to set up the system very carefully so that there is no work done by external forces. In other words, if I get rid of these two, what I find is that the total change in mechanical energy becomes zero. This is what you know as the law of conservation of energy. Now, the forms that I've showed you, the work kinetic energy theorem, way up at the top, that was for a particle. This is the work energy theorem for systems. These are big picture ideas. This is a very specific idea, and it's very, very useful for solving problems, especially here on Earth. So mechanical energy is equal to kinetic plus potential. The idea behind conservation of energy is that this sum, in other words, this value right here, is a constant. It cannot change provided you ignore non-conservative forces and you ignore forces that are outside the system. And if you're creative and clever about how you choose your system, you can often get these two to drop off. So this right here is the end of our notes. I'm not going to do any examples in this video because we're going to start with this next class period.